Hello everyone and welcome to Control Engineering Tutorials. In this tutorial, I will explain you how to design a phase lead controller or compensator in Matlab. But before I start, I would like to mention a few things. First of all, those of you who are my subscribers or who follow my work know by now that I always create a post that nicely summarizes everything that's explained in this video, and consequently here's the post. This post contains equations, graphs, and even Matlab codes. A link to this post is given in the description below this video. Secondly, it took me a significant amount of time, energy, and planning to create this video and this post. Consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start. Here's the problem. Consider the following open loop system given by the equation number 1. Our goal is to design a lead compensator such that the phase margin of the compensated system is at least 50 degrees. Now you can stop me over here and ask me the following question. Why do we need to increase the phase margin of such a system? Well, the answer is very simple. We need to increase the phase margin because we want to reduce the damping of the transient response. That is, by increasing the margin, we decrease the damping and we make the transient response to be more smooth and we make the system to be more stable. In my previous post, which can be found if you click on the link over here, I derived the main equations of the phase lead compensator, and I derived and explained the procedure for designing the phase lead compensator. In this video, I will briefly summarize this procedure and I will briefly explain you the main ideas of the phase lead compensator. After that, I will immediately explain you how to solve this problem. Consequently, let us first summarize the main ideas and the design procedure for the phase lead compensator. This transfer function over here, represented by the equation number 2, represents our phase lead compensator. There are two parameters that need to be designed. The first parameter is the parameter A, and the second parameter is the parameter capital T. Let us see the body plot of the phase lead compensator. The body plot is given over here. Let us first analyze the magnitude plot. The first thing to keep in mind and to observe is that we have two corner frequencies. The smaller corner frequency is 1 over AT and the larger corner frequency is 1 over T. The corner frequency of 1 over AT is smaller than the corner frequency of 1 over T because the parameter A is larger than 1. The next important observation is that the asymptotic gain of the phase lead compensator is 20 logarithm with a base 10 of A. Because the logarithmic gain or the magnitude plot is always positive, this means that the phase lead compensator will increase the gain of the open loop system. Let us now briefly analyze the phase diagram of the phase lead compensator. What can be observed from this graph? The first observation is that the phase lead compensator will increase the phase of the open loop system in certain range. And this is obviously because the phase of the phase lead compensator is always positive. The whole purpose of designing the phase lead compensator is to increase the phase margin. And the goal is to increase the phase margin near the gain crossover frequency of the open loop system. So we want to place this frequency over here where our phase reaches the maximum value near the gain crossover frequency of the open loop system. In that way, we increase the phase margin of the open loop system, and consequently, we reduce the damping of the closed loop system. Besides this, there are also other benefits of the phase lead compensators. You will see later on that we increase actually the value of the gain crossover frequency. This means that the bandwidth of the closed loop system is increased, and consequently we have a faster response. Okay, in the sequel we explain the procedure for designing the parameters of the phase lead compensator. The first step is to sketch the body plot of the system. Here is our open loop system. It is 10 over S plus 1. And here is the body plot. The next step is to identify the phase margin. How do we identify the phase margin? First of all, we focus on the magnitude plot. Then we draw a horizontal line from 0 decibels. This corresponds to the gain of 1. And we search for the point at which the magnitude plot of our open loop system crosses 0 decibel lines. And this is the point. Then we draw a vertical line and we search for intersection of this vertical line with the phase diagram. And here's the intersection point. Then this value over here, measured from minus 180 degrees to this value, is our phase margin. And again, phase margin is positive if this point is above minus 180 degrees. So in our case, the phase margin will be positive. In this particular case, the phase margin is 18 degrees. So this distance is 18 degrees. This is not a good phase margin, since in practice we want to have a phase margin that's at least 30 degrees. Going back to the problem statement, we can see that the desired objective is to design the lead compensator such that the phase margin of the compensated system is at least 50 degrees. Let us analyze the body plot. We obviously need to increase the phase margin around this point over here. And this point over here is called the gain crossover frequency. So what do we want to achieve? We want to achieve a phase plot that somehow looks like this, where this new value of phase margin will be above 50 degrees. From the phase margin of the uncompensated system that's equal to 18 degrees, that is, this angle here is equal to 18 degrees, and from the desired value of the phase margin of the compensated system that's equal to 50 degrees, that is, this distance should be equal to 50 degrees, and this is our compensated system, we conclude that we need an increase of phase margin of 32 degrees. So the maximum phase of our phase lead compensator should be 50 minus 18 is equal to 32. Going back to the body plot of our compensator, we conclude that this value over here should be at least 32 degrees. Here, it is instructive and beneficial to stop for a second and to plot the step response of the closed-loop system without the compensator. This graph over here shows the step response of the closed-loop system corresponding to the open-loop system without the compensator. We can immediately observe that the step response is quite oscillatory and that the damping is very small, and this is not acceptable. This is a direct consequence of the fact that the phase margin is 18 degrees. The main purpose and the main goal of the phase lead compensator is to correct this. By increasing the phase margin to 50 degrees, we will obtain the step response that's much smoother. And I can show you the step response. It's given over here. So this will be our goal, to design the system that will produce the closed loop step response that looks like this. And the magic of the phase lead compensator is that it can achieve that. Here we will stop for a second and explain the Matlab code that's being used to plot these graphs. Over here, we define the transfer function. So the open loop transfer function looks like this. 10 over s plus 1. Then over here, we plot the body plot. Over here, we define a feedback system where W of s is an open loop part, and since we have a unit feedback, and this is a negative unit feedback, we place here 1 and use this function feedback. And then finally, by using this Matlab function step, we plot the step response. We completed the step number 1. In step number 1, we plotted the body plot of the uncompensated system, and we determined the necessary correction of the phase margin that's denoted by phi m. In step number 2, we need to design the parameter A of our compensator. In my previous tutorial, I derived this equation that relates the parameter A with the correction phi m. That is, that relates the parameter A with the maximum phase of the phase lead compensator. And here's the formula. So what you need to do, you need to substitute the previously computed value of phi m in this equation. However, be careful over here because you need to transform phi m from degrees to radians, and you can use the simple formula. And the final value of A is 3.2546, and this value is larger than 1. The Matlab code for determining the parameter A is given over here, and it's self-explanatory. Next, we need to determine the frequency at which we need to apply the maximum phase of the phase lead compensator. To explain how to choose this frequency, consider this plot over here. This line over here is the magnitude of the uncompensated system, and this is the phase of the uncompensated system. This point, that is the point where the magnitude crosses the 0 decibel line, is called the gain crossover frequency. And if we draw a vertical line and search for an intersection with the phase plot, we can identify the phase margin of the uncompensated system. The phase of the phase lead compensator looks like this. And the maximum is achieved at omega m. The maximum value is equal to phi m. Our goal is to design this frequency. That is, by moving this frequency left and right, we can apply the phase lead compensator at any point. For example, if we apply the phase lead compensator over here, that is, if omega m is over here, then we will achieve this thing. And obviously, the phase will be increased here. However, the phase will not be affected at the phase margin. Obviously, a better approach would be to place our maximum phase, that is, to place omega m over here. That is, to select omega m to be equal to the gain crossover frequency of the uncompensated system. And what will happen in this case is that we will obviously increase the phase margin. By following this idea, we might come to the wrong conclusion that the phase margin of the compensated system will be equal to this value. So this is the phase margin of the compensated system, and this is not correct. The main reason why this is not correct is that besides the phase increase, the phase lead compensator also introduces a magnitude increase. Remember here that the magnitude of the phase lead compensator looks like this, where this is 0 and this is positive magnitude in decibels. Since the phase lead compensator has a positive magnitude, this means that the magnitude of the compensated system will increase in this region over here, and the magnitude of the compensated system will have this shape. That is, the gain crossover frequency will be shifted to the right. This will directly imply that the phase margin of the compensated system will be actually smaller than the phase margin we initially hoped for. So this will be actually the phase margin of the compensated system and not this. This shift of the gain crossover frequency to the right is a direct consequence of the positive magnitude plot of the phase lead compensator. Okay, so let's see how to tackle this problem. From the Bode diagram, we know that the asymptotic gain is equal to 20 logarithm with the base 10 of a. This implies that this distance over here is half of this value, so it's 10 logarithm with the base 10 of a. And since we calculated a in the previous step, we know this distance. So this distance is completely known. Let us see how this knowledge can be applied in practice. First, let us focus again on the magnitude plot of our compensator. The magnitude plot looks like this. This is 20 logarithm with the base 10 of a, and this gain over here, expressed in decibels, is known for the computed a, and it's equal to 10 logarithm with the base of 10 of a. Now, let this be a gain of the uncompensated system. And let this line be 0 decibel line. Here, it should be kept in mind that this point over here corresponds to the frequency omega m. and this is the frequency that we want to determine. Also, it should be kept in mind that we know this distance. By using this knowledge, we can simply search for the frequency on this graph for which the distance between 0 decibel points to the magnitude of the uncompensated system is precisely this distance. So if we choose our omega m here, the effect is the following one. We will basically achieve that once we add a compensator whose omega m is located over here, we will achieve that the phase margin is precisely added at this frequency. Now, by looking at the magnitude plot of the uncompensated system and keeping in mind that this distance over here corresponds to this distance over here, the magnitude plot of the compensated system will look like this. This is because this gain over here, introduced by our phase lead compensator, will compensate this negative gain over here, and we will achieve the crossover frequency of the compensated system that's precisely omega m. Now, I said here precisely. However, you should understand this precisely under quotes. That is, you should take it with a grain of salt, as you will see later that the whole procedure is iterative, because this whole idea is based on a few approximations, neglecting basically curved lines and representing them by straight lines, and by introducing few other approximations that I will not discuss over here. However, this is still a very effective method for finding the correct value of omega m. Okay, so let us apply this strategy in step number 3. Previously we computed A. We can simply substitute A in this formula and obtain our distance. Then, by looking at the Bode graph, we can conclude that omega m is 4.15. So let's look at the Bode graph just to explain this point again. Here's the Bode graph, and what we actually concluded that at some frequency over here, once the phase lead compensator is added to the system, we will achieve a magnitude of the compensated system that looks like this. Once we determine the frequency omega m in the previous step, in the step number 4, we need to select the parameter t of our transfer function of the phase lead compensator. Here's the parameter t. In my previous video tutorial, whose link can be found in the description below this video, I derived this formula for computing t. By using this formula and by substituting the value of omega m, we conclude that our t is equal to 0.1336. And here's the Matlab code for computing t. It's self-explanatory. Now, by applying the computed compensator to our system, we obtain this plot over here. So this is the magnitude and phase plots of the compensated system. Notice what happened over here. We achieved the phase margin of 45.4. It is much better than the previous value of 18. However, it's still not good enough because the requirement is to have the phase margin of at least 50 degrees. So how to tackle this problem? Well, we need to go at the first step and we need to increase the value of phi m. That is, we need to increase the necessary correction of the phase margin. By doing that, we can basically compensate the system in a much better manner. So if I increase the value of phi m to 40, and if I repeat the procedure, I obtain the parameters that you can see over here. And here is my compensator. The compensated system is shown in the figure over here. So let's analyze this compensated system. We can observe that the phase margin is 52.2, and this is the value that we were searching for. You can see how the phase plot looks like. It's very good. And let's look into the step responses. Let's see the effect. So here is the effect of the phase lead compensator. We can observe that we have much smoother and more damped response compared to the original case. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.